Okay,
Action.
think about atomic structure for a minute. You've got the electrons, negatively charged, spinning around the nucleus. And then within the nucleus you have protons and neutrons, right?
Yes.
Protons have a what charge? Positive charge. Therefore, two protons are going to do what? Attract each other or repel each other?
Repel.
They're going to repel. Like charges repel. Okay? And so, consequently, there's got to be something holding that nucleus together because it's full of positive and neutrally charged particles. And therefore, we need some other force to do that. And that is supplied by something called the nuclear strong force. Okay? Ooh. So that normally holds an atom together. Most atoms stay together, stay stable. Although all elements have at least one radioactive isotope, and when you get above 87, I believe, the larger atoms, they tend to be less stable. So some elements are almost all radioactive, and uranium is one example of an element that is naturally radioactive. So what happens is that because it's at that point where the nucleus gets so big that the repulsive forces of the protons against each other overcomes that nuclear strong force, and the atom splits apart and that force is released, and so the force is no longer with them, and therefore that energy is released in the form of electromagnetic radiation, gamma rays typically. Okay, that then comes out, and when it hits objects around them, it'll cause them to heat up. So these substances naturally give off heat. Yes?
So if I found uranium, will I get affected by that?
Yeah, I mean, if you carry it around in your pocket for a while, and then yes, it absolutely could have an effect on you. It would not be, if you had a chunk of uranium sitting there, it would not be the type, particularly if you just found like in its ore state, you know, when it's naturally in the ground, you probably would not know the difference. But certainly long-term exposure, or if you were to purify it, which of course is what they do when they make it into a fuel, then you would definitely have an issue, you know, with that. It would be a health problem from there. Correct. Uranium, very good point. Uranium is a mineral resource, comes from the ground. It's an energy resource. It's a mineral resource. It is therefore non-renewable. The good news on that particular one is the amount of it that we have in the crust of the Earth is significant enough, and the amount that is needed to be used in nuclear reactors is small enough that we don't really look at it as a running out of kind of issue with that resource. Yes, Mackenzie?
Where do you find uranium? Like obviously in the ground, but like where?
It's pretty well distributed throughout the crust. I mean, there's certain areas. I honestly don't know where the major sources of uranium are. I know we've got uranium mines in the United States. We've got them pretty much all over the world. So it's not really that limited as far as where it is. If you remember, it was the abundance of uranium in the mantle of the Earth that gives us our molten layer underneath the crust, and that's why we have an active plate surface, because the heat coming up from that keeps the asthenosphere melted. Ethan, you had another question?
Yeah. Does uranium have a benefit to the planet at all?
Well, like I said, just because we have a molten crust. We talked about the fact that having those active plate tectonics and stuff renews the crust of the Earth, and therefore, yeah, it's helpful in that respect. You know, so keeps things groovy as far as the whole plate tectonics, volcanoes, and all that kind of stuff, rock cycle kind of thing going on. So that's a good point of having it for sure. But we utilize it to utilize the energy from that, because if you take that uranium or other radioactive substance, uranium-235 is the element of choice. Notice it's got the number there. Different isotopes of different elements have different levels of radioactivity. But if you take it, what they do is they take it, they refine it, they purify it, and then they put it into these long cylinders known as fuel rods. Okay. Now, normally uranium just sitting there will give off a certain amount of energy, give off a certain amount of heat, but it's typically not enough to meet the kind of power supply that you would need in a power plant. So what they do is they incur chain reactions. In other words, they put these, they align these fuel rods in such a way that when they the atoms inside them break apart, they will go out, and since it's concentrated also, they will go out from each other and cause other atoms to break apart, and so on and so on. Now, if you do this in just the right way, you can get a large mass of it to go all at once, and that is what you have when you have a nuclear bomb. Okay, that's not what you want to have happen, of course, in your nuclear reactor. So they control that by limiting it to something called critical mass. You need a certain amount, a certain concentration, and they actually what they do in a nuclear bomb is they slam these pieces of plutonium, is what they usually use in nuclear bombs, together to cause them to all fission at once and release huge amounts of energy. That's, of course, not what happens in a nuclear reactor, but they have those chain reactions still taking place in a more limited setting, okay? And also they have control rods which can be lowered down between the fuel rods to reduce that chain reaction and therefore slow it down, cool down the plant, basically. They have it like a thermostat, so when it gets hot, they will lower the control rods and keep it from overheating and potentially causing a meltdown, which has happened once, but it was bad when it did. So we'll talk about that in a minute. So that's the basic function of a nuclear reactor. I've got a little diagram to show you in a minute to help illustrate that a little bit better. Good things about nuclear power is that it does not produce air pollution under normal operating conditions. Of course, if it does have a meltdown and you release that into the atmosphere, that would be certainly air pollution. But under normal circumstances, that does not happen, fortunately. But it is a heat-based plant, and therefore it does produce thermal water pollution. These things get very hot, even under normal operating conditions, and of course that requires a lot of water to keep it cooled down, to recycle the water and things like that. And it's discharged as hotter water. We've talked about some of the effects of thermal pollution on aquatic environments before. So that's a drawback of nuclear power, although you have that, like I said, you have that with any kind of heat-based plant, like a fossil fuel plant or something like that. But no air pollution for the most part. Nuclear fuel, it does have a rate of decay. As it decays, it becomes less radioactive. And even though it would take, really, for uranium-235, at least 1 million years to completely degrade it down so it would no longer be radioactive, it does reach a point where it's not radioactive enough to fuel the needs to heat the water sufficiently. So they got to switch it out. They got to put new fuel rods in there. They got to get rid of the old fuel rods, and those are now what we call nuclear waste. Okay, this is the big problem right here with nuclear power that we still are not sure how to deal with. Is getting rid of nuclear waste. Okay, they're just kind of letting it collect up right at this point. There's been many proposals of what to do with it. None of them are very popular or very practical. So right now it tends to sit at the facilities.
Didn't they say put it in space?
Yeah, that's been bounced off. It's a terrible idea. And I'll tell you what, if you were to, first of all, to shoot it into space, I believe would take like 10,000, at this point, 10,000 payloads. If you can imagine that many space flights, and we do, what, a couple a year at this point?
Cannon, right?
No. All right. And then second of all, we don't have that great of a track record with our space vehicles as far as them staying in the air. So you can imagine shooting up a big load of nuclear waste and then all of a sudden it blows up and falls down to the ground. That's not a good thing. So shooting it into space or shooting it into the sun is not a great, not a great solution. All right, listen up. They keep them at the place right now. What that means also is there's quite a few nuclear power plants that are decommissioned. In other words, after a certain amount of while, basically the radioactivity permeates the whole plant to the point where you can't use it anymore. But you still have that nuclear. They keep that nuclear waste there at the site, right? Because just even transporting it's a bad thing. And so at these old plants that don't produce electricity anymore, they still have a full-time security staff of people there guarding old nuclear waste.
So we need to come up with new energy.
Well, yeah, I mean, there's a lot of good things about nuclear power. This is, of course, a bad thing about it, and it's one of the problems. And that's what you guys need to know. You need to look at what's good, what's bad, etc. from there. Now, from a practical standpoint, nuclear power is extremely expensive. The plants are extremely expensive to build. Just the security and the maintenance and everything, extremely expensive. Like I just said, even after they're no longer producing electricity, you still have a lot of costs involved with it. So those are a lot of the major practical drawbacks from using nuclear energy. You, of course, also have the potential for a nuclear meltdown where the reactor core gets too hot and it melts it. Fortunately, that's only happened once, really, of note. That was Chernobyl in former Soviet Union, and it was a bad thing. A number of people died at the site, like roughly 50, and then radioactive waste was emitted all out through the countryside. A lot of people got, it's in the thousands as far as people, increase in cancer-related and other deaths from that, and contamination of livestock and all kinds of stuff. So very, very bad thing. Fortunately, very, very rare also. Yes, Carol.
There's like pictures of a place where a nuclear bomb happened or something, and the people are like, it didn't like fall apart. They're like.
Yeah, you're talking about the atomic bomb, Hiroshima.
Yeah.
Yeah.
Their
images and stuff are like against the wall. I mean, it's millions of degrees at ground zero of one of those of a nuclear reaction. So.
It's like the leftovers.
Any questions about nuclear energy as an energy resource? Yeah, Justin.
If you're right next to it, how fast can it kill you?
I don't know. That's a good question, a rather morbid question, but an interesting question. I'm not sure. I mean, if it were a nuclear bomb, you're vaporized instantly. You know, that's no going back there. Like I said, it's millions of degrees, but.
Could you imagine being vaporized?
No.
Completely vaporized in like 1 second.
You wouldn't even feel it.
Like, you'd just be like, oh, I'm done. You know, Ant-Man was like, I want to.
I've seen it twice. Okay, well.